Mutayan Sivatanu. He is a principal researcher at Microsoft Research India in Bangalore. Mutayan graduated from Wisconsin. He did work in storage systems for his PhD thesis. He misguidedly joined Google and did great work at Google before he saw the light of the day and came to us in MSR, and he continues to do fabulous work. And with that,
All right. So I'm Mutayan, as Chandu introduced. And today I'll be talking about some work we've done in building systems for efficiently training deep neural networks. Okay? So Chandu talked about both inferencing and training as two essential parts of AI or deep learning. I'll focus on the training part here. This is joint work with several collaborators, Ram, Nipun, Srinidhi, Tapan, Sanjay, Shubham, and a couple of folks from MSR Asia as well, Fan, Sean Lu, and Liron. Okay, so I don't need to introduce deep learning to you folks, especially not to this audience, not at this time. Deep learning is slated to transform entire industries, ranging from transportation to healthcare. Whether it is hope or hype, I won't get into that today. So regardless of what the future holds for deep learning, even today in reality, deep learning has already had significant impact in several products that we use almost on a day-to-day basis, right? There are some examples here: web search, whether it is Google or Bing, it's powered by deep learning in some way. Voice assistants, Cortana, Siri, Google Assistant, they're all powered by deep learning, okay? So it's clear that deep learning has already had an impact, and the question is, how do you take deep learning to the next level? How do you advance the state of the art in deep learning? And Chandu gave you a bit of historical perspective on how systems innovation enabled the recent spurt in the practical relevance of deep learning, right? What I'm going to also theorize is not only the historical perspective, but even the future of deep learning innovation depends on systems, okay? The fundamental reason for this has to do with how experimentation and innovation works in the field of deep learning or AI, okay? Because there is very little theoretical understanding of how deep neural networks work, the majority of experimentation, the majority of innovation that happens in the field is by trial and error. Let's say someone comes up with a new model architecture. The only way to know whether this architecture would actually work is to train that model end-to-end, measure accuracy, okay? Let's say you have decided on an architecture now, you need to tune the hyperparameters of that architecture. Again, you need to run hundreds of trials with different configurations and see which one gives you the best accuracy, okay? Now, each of these trials for typical models, they can take several hours, if not days, right? And so from both a dollar perspective, the cost of doing this, doing these iterations, as well as the experimentation time, systems infrastructure limits innovation, right? So fast and efficient systems infrastructure is key to the future of AI and deep learning. So today I'll talk about two systems that we have built. One is a system called Astra, which is a compiler and a runtime for running deep learning training jobs efficiently, okay? And the second is a system called Gandiva, which looks at the problem of if you have a large number of DNN jobs that you want to schedule on a cluster of thousands of GPUs, how do you do the scheduling, okay? This audience may appreciate the names a bit better. Astra, represents an arrow, which is fast, essentially. So that stands for a system that makes a single job run really fast. Gandiva, some of you may know, is a powerful bow, the bow used by Arjuna, for example, and that's an efficient dispatcher of Astras, okay? All right, so the key insight behind both of these systems is to exploit some unique characteristics of the deep learning training workload, okay? And the specific property that we're going to exploit in these systems is the predictability and repetitive nature of training, okay? What do I mean by this? So the graph on the right shows execution on a typical deep learning training job. This is a ResNet 50 model on ImageNet data. Along x-axis is time, and along y-axis we plot the amount of GPU memory consumed running that deep learning job, okay? Now, one thing you can immediately notice is the remarkable repetitiveness of that graph. This highlighted portion is essentially what is called a mini batch. A mini batch processes a group of inputs. The uptrend, the increasing line is the forward pass, and then the dipping line is the backward pass, and at the end of it, the GPU memory gets cleared. Most of the GPU memory gets cleared, and this keeps happening over and over again, okay? So if you just look at the first mini batch, that gives you a pretty good idea of how the rest of the job is going to do. And remember, this mini batch takes like 3 seconds, and that's telling you completely about how the job is going to behave for the next several hours, okay? This is a remarkable workload from the perspective of systems design because it allows you to be introspective in terms of building and optimizing a system. You can observe how the mini batch does and adapt your policies, be it compilation or scheduling, to actually fit the specific characteristics of this model. Okay. All right, so let's first look at Astra, which is a DNN-specific compiler. So here you have a single job, and you need to run that job really fast. Okay. Now, when it comes to building a compiler for any workload, including DNNs, the standard approach that people do is view the DNN job as a generic computation graph and adopt standard compiler technology. Okay. So typically, the way these compilers work is they have a model, a performance model of the underlying hardware. They have a performance model of the operators that you're running, and they try to evaluate a bunch of optimizations based on how this model predicts they will behave. Okay, and then they pick the best optimizations. This approach, we believe, is suboptimal for DNNs for two reasons. Number one, the pace at which the hardware changes in DNNs. GPU versions keep coming up every 6 months, for example. New ASICs, FPGAs come up. So the pace of hardware change is so rapid that by the time you build a very accurate performance model, it's already obsolete, right? And the same thing happens with the higher level operators as well. New operators people keep coming up with. So unlike something like databases where the relational algebra is static for decades, that's not the case here, okay? The second reason why this is suboptimal is because we believe, and as I'll show you, by making use of knowledge about this predictability that I talked about, it turns out you can do a lot better, okay? Now, Astra is essentially a multi-version compiler. So here is what a traditional compiler does. Once you get an input program, it basically enumerates a set of possible optimizations that you can apply to that program, and then it uses this performance model to rank those optimizations, and then whichever optimization is predicted to give the best performance, it will give that to the runtime, which then executes it, okay? Astra, on the other hand, does something different. The compiler now only enumerates these optimizations. It doesn't care about evaluating those optimizations. That job is now given to the runtime, okay? Now, the runtime doesn't need any performance model. It has a real system to do it. So instead of modeling how a particular optimization would behave, it actually measures it on the real system, okay? So you can think of it as, in that graph that I showed you, each mini batch will run a different optimization, and after a few thousand mini batches, you know what the best optimization for this workload, hardware would be, okay? Now, this approach of multi-version compilation has actually been tried in the past for generic programs, but it's been largely unsuccessful because of the complexity, right? When your input keeps changing, you can't make any meaningful assumptions on how a particular optimization will behave. There are statistical problems in doing that. But in this particular domain of DNNs, because of the predictability, I'll pull up this graph again, because each mini batch behaves so identically, this multi-version compilation is actually a perfect fit for this workload, okay? Now, from a compiler perspective, this has two key benefits. The first obvious benefit is the compiler is very simple, right? You don't need to build complex performance models and so on. But what is more interesting and perhaps subtle is this now empowers the compiler to be more aggressive about what I call long tail optimizations, okay? Because of how a regular optimization in compilers work, a lot of engineering goes into actually tuning the optimization, figuring out when to trigger this, how to make sure it doesn't hurt performance and so on. Now the compiler doesn't have to do any of this, right? So instead of a traditional compiler which can only afford to go after optimizations that help a majority of models, now you can enumerate an optimization that may only benefit 5% of the models, right? So you can actually do long tail optimizations. Okay, let's now get into what exactly Astra does. So I told you about adaptation, observation, and introspection. So what are the exact dimensions of adaptation? I'll give you 3 examples of what Astra does. The first one is fusion of tensor operations. The core primitive in most DNN jobs is several operations on matrices, essentially large matrices which are called tensors, okay? So let's consider this simple graph where you have 4 matrix operations going on with one shared matrix, which is A, right? You can rewrite that operation as a single matrix multiplication instead of 4 matrix multiplications if you concatenated B1 to B4 into one large tensor, okay? And you produce one concatenated output tensor. Now, it turns out, given the GPU architecture, the model on the right is much more efficient to execute because libraries such as cuBLAS do a lot better if you have large tensors, okay? Now, why do you need adaptation in this? Why can't you just always aggressively fuse? It turns out, in order to fuse this effectively, in order to get the maximum gains out of fusion, these tensors have to be allocated contiguously in memory, right? So it has interactions with the buffer manager of the runtime. So if there are conflicting choices, if B1, for example, can either be fused with B2 to B4 or with B1, you can only get one of the two because you actually have to allocate memory to fit that fusion. And adaptation helps us determine which of these two fusion choices are most beneficial for the current hardware, for the current model. The second dimension of optimization or adaptation is using multiple libraries that serve as a particular operation, in this case matrix multiplication. Okay? There are two libraries available, cuBLAS and OpenAI, and again here, depending on the exact shape of the tensors that are being operated on, one of these libraries outperforms the other. Okay? And this is another example where dynamic adaptation helps us decide on a per multiplication basis which library to use. The third dimension is managing what we call streams on the GPU. So a quick primer on the GPU execution model. The way pyTorch, Tensorflow, all these frameworks work is there is a dispatcher of kernels running in the CPU, which essentially queues. You can think of a kernel as an operation, a compute unit to be run on the GPU. So the dispatcher basically queues these kernels onto the GPUs, and the GPU services the queue asynchronously and executes them. Now, a stream provides a unit of parallelism. Within a stream, operations get dequeued in order. Across streams, they happen in parallel. So if you want to use multiple streams to expose more parallelism to the GPU, the choice of, given a new kernel, K10 in this case, which stream should you place it on, it depends on when you expect both of these queues to get flushed, which depends on the execution time of those kernels that you don't know because it's asynchronous, right? Again, this is another dimension where adaptation helps. Now, this concept of adaptation and introspection, looks all fine in theory, but one main challenge in this is how do you manage the state space, okay? Because if you're not careful, your state space can run into millions or even more. And if your training job is a few million iterations, you have to keep it within a fairly small number, a few thousand, which is what we do. So to highlight this, let's look at a simple example. Let's say there is an execution graph with three matrix multiplications in this case. Okay? Now, as I told you in the previous slide, there are two libraries for each of these multiplications. Now, with a traditional approach where you view this compute as a black box and measure only the end-to-end time, there are 8 combinations, essentially 2 to the 3 combinations that you have to measure for evaluating different interleavings of these libraries, right? What Astra does is fine-grained profiling, where instead of measuring the total end-to-end runtime, we actually measure per operation latencies, and that means you can basically navigate the state space in just 2 iterations, right? The first iteration, you run it all with one version of the library. Second iteration, you run it all with the second version, and then you do pairwise comparison of the respective runtimes, and that gives you the best combination, okay? Now, you can see how stark this problem is if instead of 3, you had 50, right? You will have 3 to the 50 or 2 to the 50 iterations in the coarse-grained approach, okay? Now, this is possible only when these operations are independent, right? Which is not always the case. One example is the stream scheduling case that I mentioned in the past, a couple of slides ago. This is the same picture from there. Again, in this case, when you're scheduling K10, which stream you schedule it on depends on what your past choices are. So your choices are no longer independent, right? So you can't adopt this fine-grained measurement that I talked to you about. So Astra uses a bunch of other techniques to do this. So on the right, we have a trace of a real DNN model training on pyTorch. It's essentially a data flow graph with data dependencies and operations. So we introduce this notion of what we call super epochs, which essentially partition the graph into disjoint super epochs. And the benefit that this abstraction gives us is we are able to reset the history of the stream by introducing artificial synchronization barriers in the stream. You essentially do a barrier synchronization on all the streams at every super epoch boundary. Okay? Now, post this barrier, when you schedule K9, for example, you don't have to worry about history because you know for a fact that history is cleared at the end of the super epoch. Okay? So we call this barrier exploration. Now, even within a super epoch, the state space is too large. You can't do exhaustive. So we further subdivide it into epochs. And instead of doing all possible combinations, we essentially adopt a greedy approach where we adapt the first epoch, and once we arrive at the best configuration for the first epoch, move on to the second epoch, and so on. And because we are able to use the actual runtime, we are able to do this greedy optimization much more efficiently. All right. In some cases, even within an epoch, you have too many operations, and we have set techniques to handle that as well. Okay, so Astra is actually implemented in 2 popular deep learning frameworks that you guys may have heard about, pyTorch and Tensorflow. And the way it's implemented is in such a way that it's surgically deployable in existing frameworks, right? We interpose at the dispatcher level of both these libraries, both these runtimes, and we can reuse the same low-level libraries that TensorFlow and pyTorch has. So the amount of extra code needed to be written for this is actually fairly small. All right, let's look at some results. So before getting into the results, it's useful to distinguish two kinds of DNN models from a training perspective. This graph plots popularity on the y-axis and performance on the x-axis. Now, really popular models such as Inception, ResNet, popular operators such as standard LSTMs and so on, there are so many models in those, using those operators that there is economic incentive for companies like NVIDIA to hand-tune optimizers, hand-tune libraries that run those models efficiently. Okay? cuDNN is an example of such a library. So these models actually run fairly well, right? On the performance scale, they actually run pretty fast. What is worrisome though is models that invent new architectures or new model operators and so on. By definition, they don't conform to the standard operators that cuDNN, for example, supports, and therefore they run really slowly, right? Often 4 to 5 times slower. But these are precisely the models where you need fast iteration, because this is where innovation happens. This is where people come up with new experimental operators and so on, yet this is the least efficient. So what Astra tries to do is bridge the gap between these popular models, essentially the hand-optimized libraries and these rare models. Okay? So let's look at some results. So this graph shows, compares the performance of native pyTorch and pyTorch with Astra on 3 long-tail models. The red bar is native, the blue bar is Astra. As you can see, we improve overall performance end-to-end by up to 2.5x for these models. Okay? The TensorFlow performance is similar, except there we have a third bar, which is the green bar that measures XLA. So XLA is a static compilation framework for TensorFlow. Okay? Now it turns out for these models, XLA actually performs worse than native TensorFlow. So if you see, the green bar is actually below the red bar. And this is because of specific implementation detail of how they handle embeddings and so on. But more broadly, this points to why it's so hard to have a static compilation policy work for this kind of a model, because you can't anticipate every possible use case that Python programmers essentially come up with at the model writing stage. Okay. So I told you the goal was to bridge the gap between long tail and cuDNN. So cuDNN is this hand-optimized library. So this graph measures performance on a popular model, GNMT, the Google Neural Translator model in this case. And the blue bar in this case, again, is Astra. Red is native pyTorch. The graph on the right does the same thing for TensorFlow. The graph to really compare with is the orange line, which is cuDNN. Okay? So as you can see, we bridge the gap between native and cuDNN, except in the case of GNMT 32 in pyTorch, where we actually outperform cuDNN. Okay? And it turns out, although this is counterintuitive, it's hard to outperform a hand-optimized library for that model. In this particular case, the 32 mini-batch configuration had a performance cliff in the hand-optimized library, right? So even for something that is, specifically hand-optimized for a particular model, it's hard to avoid these performance cliffs, and adaptation helps us get around that. Okay? All right. So that was Astra. Let's now get into the next system, which is the cluster-wide scheduler for running DNN jobs efficiently. Okay? Now, how does scheduling work today for running deep learning training jobs? The standard model is to use a traditional big data scheduler like Yarn or Kubernetes, and when a job arrives, you pick a set of GPUs to run the job in, and that job holds exclusive access to the GPUs until it completes. Okay? Now, there are 2 problems with this approach. The first is a standard problem that systems researchers have known for ages. There is head-of-line blocking, right? Let's say there is a long-running DNN job that's holding on to a bunch of GPUs. This job can take hours or even days. Now, when a short job comes in, it has to wait behind this long job because that job holds exclusive access to the GPU. Okay? Now, these short jobs occur a lot in practice because of the way hyperparameter exploration works, for example, where people try hundreds of configurations. They look at accuracy after, say, 1,000 mini batches and decide which ones to kill, which ones to prioritize, and so on. So all of these iterations become short jobs, which now wait behind such long jobs. Okay? So the standard solution for this is to time slice. You need to round robin across these jobs. But in GPUs, this is not trivial to do because GPUs are not efficiently virtualizable. Okay? And I'll tell you how Gandiva solves this problem. The second problem is low efficiency from a cost perspective. Okay? Consider the simple example. Let's say there are 2 servers, each with 4 GPUs. The red boxes indicate that the GPUs are taken. So now when a 2 GPU job comes in, the scheduler has no choice but to place them across both these servers, right? Which means if the job is communication intensive, it runs suboptimally, right? Because it has to communicate across these 2 servers. Now at a later time, 2 of the GPUs may get freed up because the job's complete. Ideally, you want to migrate the green job to the first server so that you now have co-located communication, right? Now, this is also not, always a good thing to do because different jobs have different sensitivities to locality. So you need to really know about the job to prioritize these migration decisions. I'll pull up the same graph that we looked at the start of the slide, the mini batch predictability graph, same model, right? But now let's, instead of looking at just the predictability, let's focus on this data point, right? If you look at the bottommost point in the memory usage versus the topmost point, there's about a 75x gap, right? At the bottommost point is about 300 megs, and it goes all the way up to 23 gigs, okay? And this happens over and over again with a periodicity of about 2 seconds, which is the mini batch time, okay? Now, from a time slicing perspective, because GPUs are not efficiently virtualizable, you need to move the state from GPU to CPU before suspending a job. And when you're doing that, it's much more efficient to do the migration, to do the data move when it's at its 300 megabytes mark rather than an arbitrary mark, which could be gigabytes, okay? So essentially, Gandiva uses these observations to tightly integrate the scheduler with the runtime or the deep learning job, essentially. So if you look at the colors, the interleaving of colors says that the scheduler is now more aware of the job is more aware of the scheduler, they exchange richer information, okay? The result is we can achieve much lower latencies. For example, queuing times reduced by about 4.5 to 5x, okay? AutoML or hyperparameter exploration speeds up by about 5 to 7x. And overall cost reduces by about 26%. All right. So let's quickly get into some key techniques that Gandiva uses, the core mechanisms. The first one, as I mentioned, is time slicing. So the obvious insight behind time slicing is, you have more jobs than cores. You want to run them in parallel essentially and multiplex, right? It's better than queuing. Now the times quantum we use is much higher than what traditional operating systems do. We do about a minute, which roughly translates to about 100 mini batches or so for most jobs. So the interaction between the scheduler and the runtime looks thus. The scheduler sends a suspend job to the pyTorch or Tensorflow runtime, but instead of suspending it immediately, so if you do Control Z on a process, it will suspend it immediately, right? Instead, because this framework is now aware of what the scheduler is trying to do and about mini batch boundaries, it waits. It waits until the current mini batch completes. So if you recall that graph, at the completion of the mini batch, your memory usage is like 50x lower, right? So it's able to do the move a lot more efficiently than if it was done arbitrarily. All right, the second primitive that we use is migration. You want to be able to move jobs across GPUs, even across servers. There are several motivations why you need to do migration. Handling heterogeneity among GPUs is one of those. Packing is another, where if there are 2 jobs that are both making use of maybe 20% of the GPU in terms of cores, it's better to run both of them together on the same GPU instead of time slicing between them. Okay, and this is not easy to do beforehand, because you don't know how the utilization is going to be. And here is another example where introspection helps, because you see the job running for a few mini batches, you know what the usage is, and then you can decide to pack. If after packing they don't do well, you can always undo the packing decision or undo the migration decision. Okay. So essentially, when you compare it with a traditional scheduler kicks in only at the time of job placement, okay, and then it's stuck with the decision for its lifetime, for the lifetime of the job. Whereas with Gandiva, the scheduling is introspective and it's continuous, right? It constantly adapts, it can recover from mistakes. Profiling, most schedulers do profiling, but they are limited to system-wide metrics or black box metrics, such as GPU utilization, CPU utilization, and so on. But Gandiva is able to make this profiling to be really customized to the application level, so it can measure useful work and disentangle it from overhead and interference and so on. All right, let's quickly look at some results in the 2 minutes that I have. So this Microbenchmark shows 6 jobs running on a single server with 4 P100 GPUs. Now initially 4 jobs are running, and so they all make use of 1 GPU each. Now at time 25, 2 more jobs come in, and you can see that they fairly share the 4 GPUs. So 6 jobs running on 4 GPUs with time slicing, and then once those jobs exit, the remaining 4 jobs go back to their using the full GPU. Now the blue line on the top plots the aggregate throughput, useful application throughput seen across all these jobs. And as you can see, that remains mostly static, right? Which means the overhead due to time slicing is almost negligible. So this graph shows packing in action. So look at the graph at the top. So there are 2 jobs running in this case, identical jobs. They start off being time sliced, so they alternate between each other. And after about 30 minutes or so, the scheduler figures out that they are both running at low utilization, as seen from the graph in the bottom, and it decides to actually pack these jobs, right? And as you can see, the green line, which shows total progress, grows significantly. So this data shows how hyperparameter exploration speeds up. So in this case, we run a hyperparameter search on 100 different configurations, and the far right column, has a target accuracy of 90%. So you need to find a model that reaches 90% accuracy, right? And so because we are able to explore a lot more options, a lot more configurations in parallel because of time slicing and so on, we're able to converge to that state much sooner, right? About 6x faster. This is on a full cluster. So this is on a cluster of about 180 GPUs and a real trace modeled after our workload in Microsoft. So the blue line is Gandiva's performance, and the orange line is baseline. We measure overall aggregate GPU utilization in the cluster, and as you can see, there's about a 26% gap between those. So that's the cost saving that you would get if you had Astra running on a cluster. So let me conclude by saying that both these systems are examples of how this approach of co-design or tightly integrating system layers together can yield significant dividends. The key property that both Astra and Gandiva utilize is this almost dream property that any systems researcher would love to have for his workload, which is repetitiveness and predictability across a really large time scale. Okay? And that then allows us to do adaptation and introspection. Astra uses it to try out a completely new optimization approach by adapting for every mini batch, and Gandiva uses that same predictability to exchange richer information between both the scheduler and the runtime or the framework. Okay, that's all I had. Thank you.
I saw that you compare your models or your systems with some of the existing systems, and I believe those systems are already in the commercial form available in the market.
Yes.
And yours is in the research phase in the lab, right?
Yes.
So once it comes to the market, do you see some performance, degrading because of, I don't know, when you're bringing it in the real time situation in the...
Yeah, so when you change an existing framework, right, so there are two approaches to prototyping something like this. You can either start from scratch and build something. You can build a toy model, which is a supplement or a replacement for pyTorch or Tensorflow, right? There it will have exactly the same problem because you're building something for your workload. It won't have all the error handling and corner cases and so on. But what we are doing is actually fitting it into existing Tensorflow and existing pyTorch, right? So it goes through the same code stack in some sense. So we don't expect, we plan to open source it at some point. We expect these gains to hold up even in production.
Do you have something like a figure of merit kind of a thing that, once it, comes to the commercial phase or at the process corners, that how the performance will be or things like that?
Figure of merit, I don't understand your question. What do you mean?
So actually,
let me try to answer that question, because we do have, we meaning there's an industry consortium called MLPerf that puts out benchmarks, training and inferencing benchmarks. Right now it's only training, but they'll have inferencing. Think of it as like TPCC, what you're used to. So yes, so all such systems, I hope, will go through that process.
Thank you. Thank you.
Any other questions? I think we still have a minute or two, so if I may, I'd like to ask you a question.
Yes.
So this research is posited on three things. I'll let go of the DNN part. Let's assume DNNs are here for a while. But it presupposes the existence of clearly identified points called mini batches, and right now you have a particular hardware architecture in mind.
Yeah.
How much leeway do you have if the architecture changes, and how much leeway do you really have if mini batches go away as a result of the architectural change? For example, if the mini batch size goes to 1, for example. Right. So I'm just curious.
Yeah, good question. So you're right. The predictability here comes from both the workload itself, the input distribution, so to speak, which is the mini batches, and the execution environment, which is your architecture. Now, on the mini batches, we don't depend on the mini batches being large enough. Even a single input mini batch would have the same predictability. Because as long as the structure of the DNN model is the same, you execute exactly the same sequence of computations, whether it is a mini batch of size 1 or 64, doesn't change the predictability, right? Now, when it comes to the architecture, GPUs certainly have this predictability. TPUs do, right? And unless the most of these architectures use lots of thousands of simple cores. Unless you have things like superscalar, which does out of order and so on, the predictability, if you run the same sequence of computations on the same shapes of the tensors, it should largely remain the same.
Makes sense. Makes sense. Yeah. Let's thank the speaker one more time.